A very common experimental technique that is used to determine the concentrations of an acid or base is known as a titration. Now, generically, a titration is just any experimental technique that's able to determine the concentration of a solution. We'll primarily speak of acid-base titrations, but these can be used for lots of different aqueous solutions to determine concentrations. Generally, a titration is uses reaction stoichiometry. So if you can have a chemical reaction and you know that that's going to take place, and of course we can balance chemical equation, we can use that stoichiometry to tell us how much of a reactant we have by adding another reactant. That's generally the makeup of a titration. Now, when that stoichiometric ratio is achieved, that is known as the equivalence point. And for acids and bases, that would be equal to the number of, when the number of moles of acid equals the number of moles of base. What we're going to do in a titration is we're going to use an indicator. We're going to use an indicator to tell us when that occurs, and that is known as the endpoint. That's our experimental indication when the equivalence point is reached. Usually what we're going to do is we're going to use a burette to add our titrant to the sample, and that can be either our acid or our base in this scenario. Okay, again, we're going to use an indicator to tell us when we've reached the equivalence point. And for acids and bases, that's when the number of moles of our acid, H+, equal the number of moles of our hydroxide. That's known as the equivalence point. Now, when the indicator determines that, it can slightly be different, and we'll look at a scenario for that. But the indicator tells us when we've reached the equivalence point, and that is similarly known as the endpoint. Okay, so here's what a common acid-base titration would look like. Okay, we'd have an Erlenmeyer flask in our or a sample in our Erlenmeyer flask, usually our acid. Okay, and let's say for this instance we don't know what the concentration is. Okay, into our burette we add our base or our titrant of known concentration. Now you can switch the unknown and known. We could use a base that we don't know and an acid that we do know, but let's just start out with this concentration. You're also going to add an indicator to tell us when we reach the equivalence point. Okay, we can see that from this experimental condition, I can see that this is going to be phenolphthalein as an indicator. Now, phenolphthalein is an organic molecule that's colorless in acidic solutions and pink in color in basic solutions. In basic solutions, the shape of phenolphthalein, the organic molecule, is slightly different. It causes it to start to absorb visible wavelengths of light. Okay, so what you do is you slowly add your base to your acid until the solution changes from colorless solution to a pink solution. And really what you want to shoot for is the lightest pink possible, because that will indicate that you're very near the equivalence point. You can see here in the middle slide or middle image that there's some areas of the solution that is pink. What that is it's localized excess hydroxide ions that's causing the phenolphthalein to turn pink. Usually you swirl that around and it goes away, and you keep on adding your acid until it stays pink. Okay, here's a microscopic view of an acid-base titration. Here we've got our acid in our sample. Let's say we have 5 acidic protons in our solution. We're going to slowly add our hydroxide, and of course the net ionic equation for our acid-base reaction is our acid plus our proton plus our hydroxide yields water. So for every hydroxide that's added, it will react with the hydrogen and produce a water. And eventually you'll react away all of your acid protons, and you're going to be left at the equivalence point when the number of moles of the acid equal the base. It turns out that that solution is still colorless, and so what you actually do in the lab is you add a little bit excess hydroxide, and the amount of hydroxide that you need to add to make it pink is so minuscule that it is lower than any other experimental error that you can achieve or that you will achieve doing this experiment. So generally, we assume that the endpoint is very, very near the equivalence point, and so we can use that information as our for our calculation. So what would we measure here? Of course, we would know what volume of acid we added, usually using a pipette, so we can deliver a very known, very accurate volume of acid. Okay, we know the concentration of our base, and then we add base until we turn pink. So then you also know the volume of your base that's added. And so from these, if we know the volume and the concentration of our base, we can figure out how many moles of base we added. Because we know the stoichiometry of our chemical reaction, we can determine how many moles of acid we neutralized. Then you take that and you divide it by the volume of your acid solution, and you can calculate the concentration. Okay, so let's do an example of that. Here we have a titration. We titrated 10 milliliters of an unknown HCl solution. It required 12.54 milliliters of a 0.1 molar sodium hydroxide solution. So we want to determine what's the concentration of our HCl solution. So the first thing we should do is write down our balanced chemical equation. So we know that HCl is going to react with sodium hydroxide to produce our water and salt. And we can see that sodium is going to combine with sodium chloride. So here's our molecular equation, and of course our net equation would be H plus OH minus. Okay, this is balanced, so it's a 1-to-1 ratio. Okay, so what are we going to do? We're going to figure out how many moles of sodium hydroxide we added. So if I take 12.54 milliliters times 1 liter divided by 1,000 milliliters, that will give me liters, and I'm doing that so that I can use my concentration as a conversion factor. 0.100 moles of NaOH divided by 1 liter. Okay, so now if I do that calculation, that's going to give me how many moles of sodium hydroxide I added. But if we just do one more conversion factor, a very simple one, 1 mole of HCl is going to be neutralized for every 1 mole of NaOH. This will give me the number of moles of HCl that have been neutralized. And so that's going to be 0.001254 moles of HCl. Okay, what do I want my answer to be? I want to know the concentration of my acid solution now. So I want to calculate the molarity, and that is, of course, moles per liter. I know how many moles of HCl I have. Okay, what's my volume in liters? Well, I started out by pipetting 10 milliliters of HCl, probably, so my volume is 10.00 milliliters. And I just convert that into liters, throw that up there, and that's going to give me an answer of 0.1000 liters. And so the concentration of my acid solution is 0.1254 molar HCl. Okay, so this is a very common calculation that you're going to be needing to do in the laboratory. Or any titrations, and so here's the general scheme. Okay, so we converted our volume of our titrant, sodium hydroxide, into liters so that we can use molarity as a conversion factor. So suddenly we know how many moles of sodium hydroxide. Okay, then we're going to use the stoichiometry of our balanced chemical equation. In this case it was 1-to-1, but that certainly is not always going to be the case, to convert to how many moles of acid I neutralized. Once I knew how many moles of acid I neutralized, I know my volume, throw it into my molarity calculation, and I've got my answer in molarity. Okay, let's do one more example where we are going to determine the concentration of our sodium hydroxide in this case. Okay, so we titrated 50 milliliters of a 0.1015 molar sulfuric acid solution, and it took 27.5 milliliters of the sodium hydroxide to do so. So the question is, what is the concentration of my sodium hydroxide? Okay, first things first, I'm going to write my balanced chemical equation. Sulfuric acid is going to neutralize sodium hydroxide to make my salt. This time it's going to be sodium sulfate plus water. Okay, now notice I'm going to have to balance this because of sodium 2, and then I'm probably going to need 2 waters there. Okay, so now my chemical equation is balanced. So notice now that for every 1 mole of sulfuric acid that I have, I'm going to need 2 moles of sodium hydroxide to neutralize it. So that's not bad. I'm just going to take that into my consideration. So I'm going to first determine how many moles of sulfuric acid I had. So I'm going to take my 50.0 milliliters, of course convert that into liters, and now I've got 0.1015 moles of sulfuric acid per liter. And so if I did that calculation, that's going to give me the number of moles of sulfuric acid that I have. But let's just do one more conversion factor and see how many moles of sodium hydroxide I neutralized. I know that for every 1 mole of sulfuric acid, I'm going to neutralize 2 moles of sodium hydroxide. And I got that from my balanced chemical equation. Okay, throw that in my calculator, and I'm going to get an answer of 1.0150 times 10 to the negative second. That's a 0 moles of sodium hydroxide. Alright, what am I after though? I'm after my concentration and molarity. Okay, so I've got my 1.015 times 10 to the negative second moles, and I need to just divide that by my volume, 27.5 in liters. So if I divide that by 1,000, that's going to give me 0.0275 liters, and that's going to give me a final answer of 0.369 molar.